Good morning. Come on in. Class is starting. It's not very cold outside today, but you will be glad that you're inside, that you're inside class. Because there's things we're going to figure out. We're going to start with this. We're going to look at solving equations in which the variable lives in the exponent. We said earlier that this is not a polynomial, right? A polynomial doesn't fit the pattern, because the polynomial has to be made up of terms where you've got some number times some variable raised to integer coefficients. Well, in this case, so for example, I could have 2x squared equals 200. That would be a polynomial equation. I think there's two answers for that. But this one is not fitting that pattern. It is not. This is an exponential equation, because I've got the pattern where my variable is locked up inside of the exponent, x plus 2, for example. So we said last week that one of the techniques we could consider for solving equations is this method called looking inside. And the first thing that I notice is that my bases are both exactly the same. They're both the number 3. So because the bases are the number 3, the only way these things can truly be equal to each other is if this exponent is equal to this exponent. So the technique for solving this is, because the bases are the same and the only way they're equal is if the exponents are equal, I'm just going to look inside the exponents and I'm going to write the equation 2x plus 1 must be 6 times x minus 9. Now, if I solve this, I could choose to solve this by dividing both, or I'll subtract 2x from both sides, I guess. So I'm going to take away 2x from the left. I'm going to take away 2x from the right. Did it? And then I'm going to add 9 to both sides. Adding 9 to both sides. Added 9 to the left side. Added 9 to the right side. And now I'm going to divide both sides by 4. 10 fourths is x, or I could say that x is 5 halves. 2.5. X is 5 halves. Now it's nice to check that equation and make sure, does that really make those the same? So I could say 3, and then if I want to get up into the exponent, I hit this up to button right here, right below the keypad. When I press that, it's right below the clear button. Right, can I point? Right here, there's the clear button. This is the exponent. So I've got 3 raised to the power of, and I don't need, actually, with this calculator, because it's clearly in the exponent, I don't need to use parentheses. If you have an older one where it's showing the arrow up and you're not in the exponent, you might need to use parentheses. But I can just go ahead and go 2 times 5 divided by 2. So that's 2 times 5 halves. It literally is. Plus the number 1. So when I press enter, I can see I get 729. And on the other side, I'm going to go ahead and hit 3 to the power of 6 times 5 halves, and then minus 9. And when I press enter, I get also 729. So not only does this look reasonable, right, but it does the precise thing you would expect it to do. Precisely the moment I take this value and I plug it into the equation, it makes both the left-hand side and the right-hand side 729. And because 729 is equal to itself, this is what we call a solution. So I'd like to use that technique again. It worked well. It really did. Looking inside the exponents. The problem that I have is that when I look at my bases, it turns out that 4 is not the same thing as 16. It's not. 16 is not the same thing as 4. These are not the same bases. So what I need to do is figure out a way to rewrite one of those bases so that it looks like it's a 4. And I think often students are drawn to the fact that let's use the 4 here and just say I can rewrite that as 4 squared. The problem with that is that you don't have the number 16 on this side, do you? You have the number 4. And if we replace that 4 with the 4 squared, we've just told a lie. Because when we rewrite something, we're replacing something with something that equals it. It is true, however, that 16 is the same thing as 4 to the second power. So here's where the power is. I can rewrite just that single portion of the equation. I can replace 16 with 4 squared. Your intuition might have taken you over to the 4. You might have wanted to mess with that. But here's where the power is. 16 is exactly the same thing as 4 squared. So this is a perfectly good substitution. I can replace 16 with 4 squared because they're equal to each other. The other thing that I can do is I can say, look at this. I have a power of 2 raised to a power of x minus 5. I have a power raised to a power. In fact, we have a way of talking about this on the wall in the classroom. We say if you have an x raised to an m, and then that is raised to the nth power, that's the same thing as x to the m times n. So what I can do is I can multiply 2 times the quantity of x minus 5. I can do that, and I'm going to do that. Let me rewrite the left-hand side one more time. 4 to the x plus 2 equals 4 raised to the power of 2 times x minus 5. So you can see what I've done is I've raised a power to a power. Now, at this moment in time, I now have exactly what I wanted to start with. I have a 4 raised to something equals 4 raised to something. And I know that I can proceed by setting these things equal to each other. They're going to have to be equal. That's the only way that this can be actually true. So I go ahead and I set the left-hand side, x plus 2, equal to the right-hand side, and I'm going to use the distributive property right now. I'm going to do that in this step. 2x minus 10. Let's solve. Okay, I'll take away an x from each side. I took away an x from the left-hand side. You saw me subtract it. I'll take away an x from the right-hand side. I subtracted 1x from the right. And now I'm going to add 10 to each side. Get back up here. Don't move away. 10. I added 10 to that side, and I added 10 to this side. Now I've got that x is the number 12. There we go. I think x is 12. That's what I think. I'm going to check it. I'm going to check it with my calculator friend. Turn on, calculator. Turn on. Calculator is turned on. Let's clear the calculator. So I'm going to have 4 raised to the power of 12 plus 2. I could write 14 there because that would be the same. 12 plus 2. It's a large number. Oh, but it didn't go to scientific notation. That's cool. And then on the other side, I'm going to have 16 raised to the power of 12. Whoa, get back over here. To the power of, I got 12 minus 5. It turns out there's an extra 2 that I need to delete. There we go. So I've got, this is 16 to the 7th power. What is that number? What is that number? Aha! X is exactly the value that makes the left and the right hand side the same. That's why X is our solution. Now, what just happened here is one of those things where you're going to have to look at it, and you may want to listen to that again. You may want to back it up to the very beginning of this problem and think about, we rewrote 16 as something that is equivalent to 16. Very interesting. Let's consider a final example of solving an exponential equation by rewriting the bases, because that's what we are doing. We're rewriting the bases. If you have a friend who helps you with the mathematics and they see this, they may say, let's use logarithms. Say, I don't think that's what I'm doing yet. It seems like what I'm supposed to do is solve these by just rewriting the bases. And let's save logarithms for Honors Math 3. So let's take a look at this. I see 1/4 and I see the number 2. Well, the 4 and 2 make me start thinking about a base of 2. So one of the things that I will do when I see problems like these is I might start writing powers of 2. For example, 2 to the 0 power, 2 to the first, 2 to the second, 2 to the third, dot, dot, dot. But I can also go the other way, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. And it could go up that way as well. Now, right here in the middle of the universe, right, we know that anything raised to the 0 power is the number 1. And then if I go forward, 1 times 2 is 2, times another 2 is 4, times another 2 is 8, dot, dot, dot. And if I go the other way, right, if I go the other way, instead of multiplying by 2, right, instead of multiplying by 2, if I wanted to go this way, I would be dividing by 2. 1 divided by 2 is 1/2. And yes, it's true, 2 to the negative 1 power is 1/2. It really is. It's not a negative number. This is not negative 2. This is 1/2. And if I divide by 2 again, I get 1/4. 2 to the negative 2 is 1/2 squared, which is 1/4, and this is 1/8. The reason why I like this is because I've just identified what I'm going to do. I have the number 1/4. I have the number 1/4, and I know that I can rewrite the number 1/4 as 2 to the negative 2nd power. They're the same. It's a valid substitution. I can rewrite this equation not with a 1/4, but as a 2 to the negative 2nd power. So let's do that. Let's go ahead and write 2 to the negative 2nd power raised to the 3x minus 2 power. And that should equal 2 to the x plus 5 power. I'm closer, but I'm not exactly where I want to be. I have a power. Let's say that this is just x raised to the m. I have a power raised to another power, and I know that that's the same as x to the m times n. So I'm going to go ahead and multiply this value, negative 2, times the quantity 3x minus 2. And when I do that multiplication, I get 2 raised to the power of negative 6x plus 4. And on the other side of that, that equals 2 to the x plus 5 power. This is a wonderful thing. It's a wonderful thing because, first of all, I legitimately replaced the number 1/4 with something that totally equals 1/4, right? 2 to the negative 2nd is exactly the same thing as positive 1/4. I can look at that on my calculator and confirm it. and I'm starting to understand negative exponents. But even more importantly, right now, I have an equation where my bases are both 2. And because the equation I have the bases are both 2, I know that the only way that these are truly equal is if that exponent is equal to this exponent. So looking inside the exponents, I can say, let's solve this. This is going to become negative 6x plus 4 equals x plus 5. Okay, let's see. Let's take away, this time, let's take away 4 from each side. I just subtracted 4 from both sides. That's what I did. I had a 4 on the left, and I had 4 more on the right, but I took 4 away. Now I'm going to subtract an x from each side. Okay, if I subtract an x from the left-hand side, this is going to become negative 7x. And if I subtract an x from the right, it's just the number 1. So now I'm going to divide by negative 7. X is negative 1/7. I want to check that answer, and I bet you want to check it too. So let's go to our friend the calculator, and let me show you a trick I like on the TI-84s. I'm going to enter negative right there. This button right here lets me hit negative 1 divided by 7, and I'm just going to press enter. This decimal and even more digits that are unseen, that's the number 1/7. And I can get up and use that again without having to type it again. So let's go ahead and take this base. I've got 1/4. I will use parentheses here. 1 divided by 4. Close the parentheses. I'm going to raise that to the power of 3 times. I'm going to go get the x by hitting the up arrow, pressing enter. Oh, that's a mess. And then minus 2. When I press enter, I get, you can see the digits. You can see all of them. All I need to see is it the same thing on the right hand side? 2 raised to the power of, let's go get that fraction 1/7. Can I get it up here? Let's not risk it. I think I can. Maybe I will. Oh, that looks better, doesn't it? That's negative 1/7 plus 5. Enter. You see what I see? 28.9315. All the digits. All the digits on this display are the same. You know what we did? We found the value of x that makes the left-hand side equal to the right-hand side. We found the solution. We only have 2 more problems we're going to do. Just 2. So you already have 3 in your notes. We're going to do 2 more, and this is one of them. Here it is. When I see this, I have a momentary panic because I don't know how to deal with square roots in an equation. However, if I consider looking inside, if I consider what does this have to be such that when I take the square root, I get an answer of 7. And I know because sometimes when I'm not bored, but I want something really exciting to do, I might just start squaring numbers. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and I can go on. But this goes both ways, right? You can see if I square 7 and I get 49, it turns out the square root of 49 would give me the 7. I know that this thing inside, if I'm looking inside the radical symbol, this must be the number 49. Because if it was the number 49, and I took the square root of it, then I would get the number 7. So I'm just going to say to myself, well, what would that have to be? What does x have to be to make this 49? Well, I don't have to just say it. I'm going to do this. I'm going to force it to be 49. I want 2x minus 1 to be the number 49. That means that 2x has to be 50. That means that x would be 25. So if x is 25, I get the 49. And when I take the square root of 49, I get the 7. I don't even need to check it because I just checked it. X is 25. And for our final problem today that I would like for you to think about and record in your notes, we talked last week about solving using fraction busters. And if I take a look at this, I have two fractions here. I've got a fraction of 2x and I have a fraction with a denominator of 2, right? One denominator is 2x, one denominator is 2. This equation has three terms. There's two terms on the left hand side, and the right hand side has a single term. And what we are going to do is we are going to push across a value that will bust all of those fractions up. And it turns out the value we're going to use is 2x. 2x will obliterate the two fractions that I see. So every single term is going to get a factor of 2x, starting with the 12. 2x times 12 plus 2x times 5 over 2x equals 2x times 7 over 2. Was that too much work? I don't know. I wrote it down. It's nice because I can verify visually that, yeah, this got a 2x, this got a 2x, this got a 2x. Every single term picked up a factor of 2x. Okay, what do I get if I simplify this equation? Well, let's do that. This is going to become 2 times 12 would be 24x plus, a giant 1, 2x over 2x, which means this just becomes the number 5, equals, you can see it, I can see it, we can see it, 2 over 2 is also a 1, so over on the right hand side we're left with 7x. To solve this, I'm going to take away 7x from both sides. I think that's what I'm going to do. When I take away 7x from the left hand side, this 24x is going to become 17x plus 7. And when I take away 7x from the right hand side, I'm left with nothing. So I put a 0 there to remind me that there's still two sides of this equation. One of the sides is just 0 now. Now I'm going to subtract 5 from both sides. I just did it from the left hand side. There was a 5, I subtracted it. Now I'm subtracting 5 from the right hand side. And finally, I'm dividing both sides by 17. My answer is negative 5/17. And I know what you're thinking. You don't like that answer very much. It doesn't look like a nice answer. To which I say, yeah, it is kind of goofy, but fractions are numbers too. So let's fire up our calculator and see if this works. Okay, let's do that. Same thing. I think this time I'm going to go ahead and enter the negative 5 divided by 17, and I'm going to leave that on, not 12, divided by 17, and I'm going to leave that up on the screen there. Now, on the left hand side, I've got 12 plus 5 divided by. Now I got to be careful. This denominator has a product. It has 2 and it has an x. And order of operations will just divide by 2 and then multiply the whole thing by x if I don't specify that what I'm about to type is the denominator. So I've got 12 plus 5 divided by, and then I have open parentheses 2 times, let me go get that fraction, I'll get it right here, got it, close the parentheses and press, it should be 3.5, it is 3.5. it is 3.5, and 7 divided by 2 is also 3.5. So although it's not the prettiest answer in the world, right, it is the answer that made both the left hand, the right hand side, the left hand side and the right hand side equal to 3.5. So it's our solution. As you work today on your homework, please take time and make sure that you're showing these steps. If I go back and I look at the work that I've done for these, for every single one of these, right, I can see the work and I can see the steps that I have taken and I can see the results. If I look on your paper, remember this is in the course syllabus, and all I see are answers, 5/2, 12, -1/7. You're not doing algebra and you're not communicating. Mathematics is a language, and the goal is for you to get good at communicating with it. So please make sure in the review preview today that you're showing your work. This is Mr. Roberts. Look forward to seeing you in class and again online. Have a great day.